Today we're excited to welcome a team of researchers from the Geological Survey California Volcano Observatory. For the past several years have been studying the volcanics of the Clear Lake volcanic field. Today we have with us a research geophysicist, Michael Mitchell, volcanic hazards and communication specialist, Jessica Ball, research geologist, Seth Burgess. Michael focuses on using gravity, magnetic, and MT databases to better understand the magmatic plumbing of the Clear Lake volcanic field, characterize the volcanic hazards, and elevate the threat of the Clear Lake volcanic field poses to nearby communities. He holds a Bachelor's of Science in Geophysical Engineering from the Colorado School of Mines, a Master's of Philosophy in Earth Science from the University of Cambridge, and a PhD in Geophysics from the University of British Columbia. Jessica is a physical volcanologist who specializes in volcanic stability and associated hazards, as well as a volcanic hazard modeling and communication. She leads activities in the intersection of hazardous research and risk communication, translating volcanic hazard information to policymakers, civil authorities, and the public in California. She holds a Bachelor's of Science from the College of William & Mary and a PhD in the University of Buffalo. Seth is a research geologist specializing in accessory mineral geochronology. He is focused on the application of uranium-based geochronometers and date volcanic rocks for the purpose of accurately determining the timing of voluminous eruptions and for constructing comprehensive eruption histories of long-lived volcanic systems, characterized by the potential future volcanic hazard. He holds a Bachelor of Science in Soil Science from Cal Poly, a Master's of Science in Geology in the San Jose State, and a PhD in Geology from MIT. Please welcome Michael, Jessica, and Seth.
Hi, I'm Seth. That's Jess. That's Mike Mitchell. And we're going to do something a bit different than the first talk. We're going to kind of take you through some Geology 101 if you never took that. You're about to in 20 or 30 minutes or so. We work for the California Volcano Observatory, which is under the umbrella of the Department of the Interior and the US Geological Survey. And we are charged with understanding the volcanoes in California and how they might impact the infrastructure and the people that live in California from a hazards perspective. So we do fundamental research science to inform ourselves as to what might happen in the future with respect to California volcanoes. There are active volcanoes in California, and we classify their activity based on how recently they have erupted, how close they are to population centers, whether or not there are lots of flights that go through that area each day. And believe it or not, Clear Lake counts as a quote-unquote high-threat volcano under the eyes of the USGS volcano observatories. And as a result, in the late 70s, quite a bit of work was done in the Clear Lake area trying to understand the potential for geothermal production here. Obviously, you're all familiar with the geysers. And a lot of that work kind of informed our understanding of the life cycle of the Clear Lake volcanic field, but not a lot has been done since then. So if you look at our publications from the USGS, on the hazards of the Clear Lake volcanic field, there's just kind of a big ellipse over the area. It's not a very nuanced hazard assessment. So we figured that it would be a good time because since the 1970s, there have been significant advances in analytical techniques, and we're able to build a much more nuanced hazard assessment of the volcanic field. So for the last few years, we have been out here banging on rocks, trying to understand the volcanic field. The Clear Lake volcanic field is not alone, it's non-unique in California. There are a series of volcanic fields stretching in time and in space all the way down to San Luis Obispo. Anybody ever been to Morro Rock on your way to taste those Paso cabs?
It's okay.
That are doctored, evidently? Morro Rock is about 30 million years old, and it was erupted as a result of the same tectonic setup as Clear Lake. So there are three major plate boundaries in tectonics. So the first is called a convergent plate boundary, and this is where oceanic crust to the left is subducting beneath continental crust, which is what's on the right of that block diagram there in the middle. And when you subduct ocean crust beneath a continent, you can promote melting in that downgoing plate, and above the melting zone on that downgoing plate, you get volcanoes. All the cascade volcanoes that we see, that I show on that diagram to the right, are a result of a subduction zone and this convergent plate boundary. So keep that in your mind. We're going to go to the next one. Instead of shoving plates together, we can pull them apart, and volcanism occurs when you pull plates apart because it allows for melt to propagate up from depth. And so this is a spreading center tectonic boundary, and you can see the East Pacific Rise and the Mid-Atlantic Ridge are both examples of that are enormous, but there are also much smaller spreading centers throughout the oceans, and it's a place where we build new crust. The next boundary, and next slide, is a transform boundary. You're all Californians, or at least sitting in California today, if from elsewhere. California is characterized by a world-famous transform boundary, the San Andreas Fault. Separates the Pacific and North American plates when they slide past one another. So those are the three different tectonic boundaries, and they don't have to occur in a vacuum. They can interact and do interact with one another. And the reason the Clear Lake volcanic field is here, and the reason all these other volcanic fields stretch south to Sonoma, or to San Luis Obispo, is because of the interaction of these plates. So let's go to the next slide. This is the current tectonic setting of Western North America on the left. The long red line cutting through California and labeled San Andreas Fault is the San Andreas Fault. There's a subduction zone north of that. It's got the little teeth on it where the Juan de Fuca plate is being shoved beneath the North American plate. We get volcanoes there, the Cascade volcanoes. And then right off the Mendocino fracture zone, between the Pacific plate and the Juan de Fuca plate, there's a spreading center. So we have all three of those boundaries now to the north of us in coastal California and southern Oregon. So you can see on the right-hand side a three-dimensional version of that where the Juan de Fuca plate is being subducted. The Pacific plate is diverging from that subducting Juan de Fuca plate. And just south of that, not shown in the diagram, we have the San Andreas Fault. All right, now, surprisingly, I'm going to put this all together, I promise. So before we play the video, if we can play the video, just below where it says Farallon plate, you see the little crinkle right there? I want you to focus on that spot. This is what California coastline looked like 30, or actually 40 million years ago. So on the far right, there's a timeline. 40 million years ago to the present. And when we click go on this, you'll see the evolution of this tectonic environment. And when that spreading center on the left-hand side of the Farallon plate contacts Western North America, one side of the spreading center falls underneath the continent. And when it does so, it opens a gap in the lithosphere through which melt can propagate. So instead of getting volcanoes way down inland like you do in the Cascades, you end up with volcanoes very near the coast because of this thing called a slab window. Okay. So hit the video and let's see if it plays. Ooh, look at that. Okay, here we go. So 30 million years ago, boom, at San Luis Obispo, you contact and you start making volcanoes. As the San Andreas Fault grows through time, that triple junction, or the nexus of those three plates, travels north. So there's Baja separating, and at the present, we look just like that. So over 40 million years, the San Andreas Fault has grown. That transform boundary has lengthened as subduction has been pushed northward. So we no longer have subduction zone volcanoes in California. They're all up in Oregon because that triple junction, the nexus of those plate boundaries, has moved north. Somebody nod at me. Yes, okay, good. So can we play that again, just for fun? So 30 million years ago, bang, San Luis Obispo. And as that plate subducts and breaks away, you get melt coming up through. And instead of generating volcanoes inland, like as inland as Shasta, we generate them along the coast of California. Clear Lake is one of those. All right, next slide. So there are lots and lots of volcanic rocks associated with this migrating triple junction. And every dot on that map is some nerdy geologist out banging on rocks saying, well, there's one here, put it on the map. And these are all the ones south of the Bay Area, and they range in age from about 30 million years ago to the present, or 30 million years ago to 10 million years ago. Younger than 10 million years is where we're standing now. Let's go to the next slide. So here they are. San Luis Obispo is hazy down there at the bottom. You've heard of the Pinnacles. That's one of these. The Berkeley Hills, if you go down toward Berkeley and you look up at those beautiful, it looks like Napa Valley just shoved down there, the big cliffs above Berkeley. That's this stuff. It's about 15 million years old. The Sonoma Volcanic Field, Mount St. Helena, is one of these. It's about 2.85 million years old. And the Clear Lake Volcanic Field is the youngest and the northernmost of them all. And it ranges in age from about 3 million years old to as young as 8,000 years, which geologically is quite young, which is why we're getting paid to be here and study this stuff. So that is the chain of volcanoes that has been in place as that triple junction migrated northward. Cool? Let's go to the next one. So the Clear Lake Volcanic Field is not characterized by big explosive eruptions. It's mostly lava domes, small lava flows. And although it would pose great risk to the local population, it's not so much of a risk more broadly. But just to the south, the Sonoma Volcanic Field is characterized by big explosions. The stuff that makes up Mount St. Helena, which has been uplifted along a fault and exposed for us to see, is what's called an ash flow tuff. It petrified the forest that you can see over near Calistoga, and it erupted explosively and in great volume, greater volume than anything at Clear Lake. And it sent ash all the way down to Bakersfield. So if something like that, and that happened 3 million years ago, if something like that were to happen today, we'd be in trouble. So Clear Lake has been erupting for about 3 million years. The Sonoma Volcanic Field had been erupting for about 5.5 before that big eruption occurred. So we really want to understand the relationship between Clear Lake and Sonoma and the life cycle of this volcanic field to ascertain whether or not it's on its way to a big eruption or is likely just to continue as business as usual. Next slide. So the Clear Lake Volcanic Field sits where it sits because it's between faults that are associated with the San Andreas. Movement along these faults creates space in the crust for magma to reach the surface. And so we sit in this fault-bounded basin, and that controls the location, primarily, of the volcanic field. So the faults are labeled on the left. The map on the right shows the Clear Lake Volcanic Field volcanic rocks in green, stretching from Canocti and High Valley on the northernmost part, all the way down damn near to Berryessa. All right, so here's the geologic map, and we have some of these out front that you can look at, and they're free to download online. I know this is what you all want on your bedroom windows or bedroom walls. As I said, it was mapped in the 70s, focusing on the geothermal potential. We got about 12 cubic miles of total volcanic rock. It's been going on since about 3 million years ago, although not continuously. It erupts in what we think are episodes of high volume eruptions separated by periods of relative quiescence. And it's characterized by volcanic domes. Mount Canocti is a series of volcanic domes, sort of like toothpaste, of subtly different compositions squeezed off over maybe tens of thousands to 100,000 years. And Clear Lake is generally younger to the northeast, so the oldest rocks that are around 3 million years old are those down by Lake Berryessa. Those rocks out on Butts Canyon, up on the tops of the ridges, those are all 2.5 million year old basaltic andesites. And it ranges young all the way north. The rocks in High Valley that you've all planted grapes on are some of the youngest lava flows in the whole field. They're somewhere on the order of 8 to 10,000 years old, but we haven't directly dated them. We're working on that. Next slide. So I think I've well motivated why we're interested in studying the Clear Lake volcanic field. It has the potential to end up looking like the Sonoma volcanic field. It's a populated area, and it's the closest young volcanic field to the very densely populated San Francisco Bay Area. So, next slide. So what are we doing out here other than driving around in a blue truck, knocking on doors, and asking to bang on rocks in your lovely vineyards? We've got a bunch of different people at the USGS on. Well, there's 5 or 6 of us on this team, and each of us does something more nuanced than the next. So I'm, as you heard, a uranium-lead geochronologist. I date rocks. Mike does geophysics. Jess does physical volcanology. And we have people doing other things as well. And so Mike and Jess will talk in a bit more detail about their work specifically, but I thought I'd give you just a flavor of the stuff that we're doing out here as fundamental science, trying to build our understanding of the potential for future volcanic hazards. So let's go to the next slide. And all of those yellow dots are places that we have been and bagged a little bag of rocks. So we're all over the place in our little blue Ford Ranger and have been for the last few years. Let's go to the next slide. So here are some of the spots we've been. You'll likely recognize some of these. The one in the bottom middle is out on the Langtree Estates, and they've been spectacular to us, and they're busy bees out there, and it's wonderful for us because we're used to banging on mush, weathered rock at the surface, and that's not what we want. We'd much rather you guys take a D8 cat out there and plane off an entire lava flow and pack all the big, beautiful, nice boulders to the side so we can just drive up to them and swing a sledgehammer. So we're forever indebted to the folks that are putting in vineyards out here because it gives us a window in the subsurface and a quality of rock that we would otherwise never be able to get near. Let's go to the next slide. So we'll just talk. You can click again. Hopefully this stuff will show up. Yeah, just keep clicking until everything's there. Perfect. So this is a simple plot of magnesium versus silica. And in red are rocks from Lassen, but all the other symbols, all the circles are Clear Lake rocks. And so we span the compositional range of erupted igneous rocks, from things that are really rich in silica, like 75 weight percent silica, to things that are 45 weight percent silica. A range in magnesium and iron and all the major elements and all the trace elements. So we kind of run the gamut. And we've got a really smart gal that is teasing out the subtleties of this geochemistry, trying to understand where these rocks were made in the crust, why they erupted the way they did, and whether or not there are any patterns in space and time as to the chemical composition of the rocks erupted, because that tells us something about what's happening at depth and what might happen in the future. Let's go to the next slide. As I said, we're also doing geochronology. We're trying to build an eruption history for the volcanic field, understanding what happened where and when. And so the colors on the volcanic field map here are just broad groupings of when things have happened. As I said, it youngs generally to the northeast. Let's go to the next slide. And here's all the rocks we've dated. That's age in millions of years on the vertical axis, and the horizontal axis is unitless. It just shows the samples ranked by time. So each of those dots is a rock that has been dated either by argon-argon geochronology, sort of like carbon dating, but with using isotopes with much longer half-lives, so it's usable for rocks of this antiquity, or uranium-lead geochronology, which is what I do. So we've dated lots and lots of rocks trying to put together the eruption history of the field. Let's go to the next slide. We also have some folks doing what's called paleomagnetism. As a rock cools from a melt, the magnetic minerals in that rock align with the North Pole, just like a compass, and it locks it in. And so the North Pole precesses slowly. There is what's called secular variation. And we know about the rate at which that precesses. And if we presume that rate has been constant over time, we can drill a section of rocks, look at how much the secular variation varies in those rocks, and get some idea as to the longevity of eruption. So if you've got a stack of lava flows in that triangle, with A being the oldest and D being the youngest, if they all erupted within, let's say, 100 years of each other, on a secular variation plot, which is what you see on the bottom, they're all going to plot right on top of each other. If there was 100,000 years between them, it's going to be scattered all over the place. Let's go to the next slide. So that is what Konocti looks like. Much of Konocti built on the 1,000-year time scale, maybe even shorter. Some of it scattered around, so it's kind of a big pulse of dome building, and then a few bits and bobs here and there. Kind of cool work by a couple of our colleagues. Go to the next slide. This is what the rocks out to the southeast of the field look like. Those older basaltic andesite rocks that are covered in vineyards now stretching out toward Berryessa. They are scattered all over the place. And that makes sense because the radiometric geochronology that we've done suggests that those rocks erupted from about 1.4 million years ago all the way back to about 3. So very long-lived, small volume eruptions that have since been dissected by faults, which is in great contrast to the big volume eruptions of something like Konocti. Next. So I'm going to shut up, and hopefully I've motivated well why we're out here and kind of the breadth of stuff we're doing. Mike is going to talk about geophysical surveys and trying to image what's happening beneath the ground. Go for it.
Thank you all for your attention here. So like Seth said, I'm mostly working on the geophysical side of this project, and geophysics is a lot like medical imaging. We take some sort of a physical field that's coming in, it interacts with the subsurface, and then we record it at some sort of station. And based on the change from what's coming in to what we record after it's interacted with the ground, we can build up like a three-dimensional model of the distribution of some of these different physical properties in the subsurface. And so we can use a number of different techniques. We can look at gravity, we can look at magnetotellurics, we can look at like airborne magnetic inversions, and each of these different techniques is sensitive to a different physical property of the Earth and gives us kind of a different picture as to what's going on. So then if we can pull many of these different methods together, we can do what's called like a joint inversion, where we can build one model that takes into account the contributions from these different methods and give us one model that can accurately reproduce all of these different data. So I guess this on the slide here is a picture from the geysers geothermal field just south of us, and you can see all of the steam, some of it rising from fumaroles in the near field and then other from the power plants. So we know that there's still a huge amount of heat in this area, but the big question is there still molten rock at depth that we need to be worried about erupting? So we're really trying to image any zones where this molten rock has accumulated in the subsurface, and we're going to try to use geophysics to get at that. Next slide, please. So here's just a little bit of background information. For these geophysical methods, we do something with the data that's called geophysical inversion, and that's basically just trying to work backwards from the data on the right-hand side of the screen to produce a three-dimensional model of the subsurface that tells us kind of what's going on in terms of the physical properties. And to do that, we first have to break the subsurface up into a mesh of all of these little cells. And then in the inversion process, we're going to change the physical properties of each of those little cells until we both fit our observed data and we have a model that is geologically reasonable. So there's kind of those two parts that we're trying to balance, making the model geologically reasonable, but also having it reproduce the measurements that we're making out in the field. Next slide, please. So we're going to start with gravity data. This data has been collected in this area all the way back to the 70s, so we've compiled a large data set of about 3,000 gravity measurements. With a gravity measurement, you're basically just measuring the vertical component of the gravitational force that's pulling on the instrument right there at that one location, and using that, we can kind of highlight density contrasts in the subsurface. So if you have, let's say, some sedimentary rocks that have a lot of pore space, those rocks are going to be less dense than maybe a basaltic, very mafic, volcanic rock that's very dense and doesn't have a lot of pore space and has heavier minerals. So we'll be able to see the contrast between those different types of rocks in our inversion. Next slide, please. So previous studies have identified this large regional gravity low that's centered about Mount Hannah and the geysers that's circled in red over there. All those little green squares on the plot are showing the different power plants in the geysers, so that's kind of delineating that general geothermal field down there. And historically, there have been kind of two main interpretations to try to explain this regional gravity low that's been observed. The first, and probably the more popular one, is that there is some sort of a mid-crustal magma reservoir at depth where we have some of these molten rocks that have accumulated. And since they're partially molten, they have a lower density than the crust surrounding them. An alternative explanation that was put forward in the 90s said that, well, we might not need this partially molten rock. We could maybe explain the gravity low with just a really thick sequence. 5 to 7 kilometers would probably be about 4 miles thick. So a 4-mile thick sequence of sedimentary rocks that are part of the Great Valley sequence. So part of what we're doing with this gravity inversion research is trying to discriminate between those two hypotheses that have been put together and see if we can shed any light on which of them kind of holds more weight. Next slide, please. So here's some of the results of our gravity inversions. This is a kind of a cross-section that goes from southwest to northeast across the area, cutting through the geysers, Mount Hannah, and then extending up towards, just extending out across the Berryessa Fault and up that way to the northeast. And we see, the main thing that we see here is there's a density low beneath Mount Hannah, and then there's a little bit of an intermediate density low beneath the geysers, which is probably the intrusive rocks that sit beneath that geothermal field, so basically volcanic rocks that have been injected into the crust and have cooled underground. So those rocks are still a little bit less dense than the surrounding rocks, but they probably don't have a whole lot of melt left in them, so they have kind of this intermediate density. And then at depth, like 6 to 12 kilometers depth between the geysers and Mount Hannah, we see this larger low density zone that we're interpreting as a zone of partial melt in the subsurface. Next slide, please. And so then how can we are there things that we can compare those inversion results to verify, to make sure that they're geologically reasonable? And one of the first things that we can turn to are geothermal borehole logs. And so on the right there, you see kind of a lithologic interpretation of one of these boreholes, and then just to the left of it is a log of density. And the main thing that we see in this well was drilled kind of right between Mount Hannah and Mount Canocti. In green there, you see this sequence of Great Valley rocks, which was kind of that secondary hypothesis. They were saying that maybe if you had like 4 miles of these Great Valley sediments, you could explain that gravity low. But in our borehole logs, we see that we only have a thin layer of these Great Valley sedimentary rocks. In this case, it's only about 500 meters thick. So this kind of shoots a hole in that whole hypothesis that we have this huge, thick package of sedimentary rock sitting there, because we don't see it in the borehole logs. So we have to kind of invoke something else that's deeper than these borehole logs to try to explain our low density. And then at the very bottom of this well, there are a number of different mineral assemblages that we see down there that show evidence of contact metamorphism, which is basically when you have melt injected into the crust in this area, and it heats up the rock surrounding it, and that heat and pressure alters the minerals that are in that rock. And so we see evidence of these intruded rocks at maybe a depth of about 3 to 3.5 kilometers. And so this shows that kind of between the area between Mount Hannah and Mount Canocti, there may be an area of intrusive rocks that is mostly solidified, kind of like we have underneath the geysers. And both of those systems may be being fed by this larger partial melt zone that we see at deeper depths of 6 to 12 kilometers. Next slide, please. So this is just kind of pulling everything together. The top is, again, our results from the gravity inversion, and the bottom is kind of a stylistic or an interpretive cartoon that we made to try to explain what's going on with the geology. We have some of the more basaltic or mafic melts in the lower crust, and then kind of in those mid-crustal levels, we have the more silicic partial melt zone, and that partial melt zone is then maybe feeding a pluton that sits underneath Mount Hanna and extends out towards Mount Konocti, and then may also be providing heat into the bottom of the geyser's plutonic complex, which provides a heat source for that geyser's geothermal field. Next slide, please. And so, with any of these geophysical methods, they all have kind of blind spots. They all have things that they're not good at resolving. So by looking at different geophysical methods and combining the results, we can get a more holistic picture as to what's going on. So over the last 2 years, we've been going around collecting a new magnetotelluric data set, and a lot of you have been hugely helpful in that effort because you've given us access to your vineyards and property where we can set out these instruments and let them record data overnight. So magnetotellurics is a natural source electromagnetic method, and so what we're doing is we're putting out a series of 3 magnetic field coils which measure all 3 components of the magnetic field, so a north-south, east-west, and then a vertical component of it. And then we're setting out 2 pairs of electrodes which are measuring variations in the electric field, and those are oriented north-south and east-west. And we set those out and we allow them to record for like 18 to 24 hours. And in doing so, we're able to measure how those different fields are varying over a range of different frequencies. And that's going to be important because each of those different frequencies are going to give us information about a different depth in the subsurface. And with the gravity inversions, where we were interested in a physical property of density, here we're backing out the electrical conductivity of the surface. So how easily electric currents are able to flow through many of these different rocks. And again, if we have partial melt down there, those electric currents are going to flow easier than they would in the absence of some sort of a fluid or a partial melt. Next slide, please. So this is just a picture of what some of our instrumentation looks like. This is our colleague Jared Peacock. And so at the bottom, you see some of the magnetic field coils. They're about the size of a baseball bat. And then next to those are some of the electrodes, which each have like a 50-meter long coil of rope. And then in the middle that Jared is standing over is kind of the control box and the battery that powers the little control box where everything is recorded. Next slide, please. Here's just some of the pictures of the installations. So for the horizontal magnetic field coils, we have to dig a trench that's maybe like 4 feet long, 6 inches wide, and 6 or 8 inches deep. And so each of those coils, the north-south and the east-west ones, have to be put in pointing directly east, south, and northwest, and then they have to be perfectly level. And then the vertical one, it's not always possible around here to dig like a 3 or 4 foot deep hole and stick this thing in, bury it completely vertical. So many times we have to tie it to a big rock like that or a tree or something like that. And then the electrodes are easier to deploy. They're just a little hole that's about the size of like a large pop can and about 6 or 8 inches deep. And we pour a little bit of water in there to kind of improve the contact resistance that the electrode has with the surrounding soil. Next slide, please. So here's a map that's just kind of showing the distribution of these MT stations that we've put out over the region. You'll see a large cluster of them in the geysers. We've had an ongoing project there for the last 2 or 3 years where we've gone back and reoccupied the same stations once per year to try to measure any changes in the steam field. And then the other ones are part of the broader project to try to image the magmatic plumbing beneath the Clear Lake volcanic field. So you can see that we've cast a pretty wide net, and we're really starting to fill in most of the gaps in our data coverage, but we still have some holes that we're looking to fill just to make sure that we don't have any kind of blind spots where we're missing data coverage. So you guys have been hugely helpful in filling in all of these holes. We really appreciate your interest and having the opportunity to work all of you to make this happen. Next slide, please. Here are some preliminary results from some of these MT inversions that we've done so far. You see, so in this one, the blue areas are more resistive and the reddish colors are more conductive. And so underneath Cobb Mountain, you see this fairly bright or dark colored blue anomaly, which correlates with the geysers plutonic complex, which are these very resistive, intrusive igneous rocks that have mostly cooled beneath the geysers geothermal field. And then right across the Colomi Fault, from that, underneath Mount Hanna, you see an area which is much more conductive. That's very close to that area where we were seeing the low density anomaly in the gravity results. And you see that this seems to be maybe part of a larger structure that is maybe extending out to the northeast as you move out towards Round Mountain in High Valley and up towards Wilbur Springs in that direction. So more work to be done on this, but initial results are largely corroborate the work that we did with the density and the gravity inversions. But there's definitely an interesting anomaly out there to the northeast that we need to investigate further. Next slide, please. Here's just kind of a comparison of a bunch of different studies. Published this last year in the literature, we found a seismic study of this area and their inversion results are in the top panel. We have in the top left, there's a P wave velocity, which is kind of the speed at which compressional waves travel through the Earth. And then the upper right is a VS, or a shear wave velocity plot. And so those particle motions are more of a shearing motion than a compressional motion for those waves. And you can just generally see there that there is a very large amount of agreement between where we see low seismic velocity anomalies and our low density body, which is what you would expect if you had some sort of a fluid or a partial melt zone. Those seismic waves are going to travel slower through that partial melt than they would through solidified, hard, competent rock. And then for comparison, there is the resistivity plot from our MT inversions in the bottom left there. And that is that's showing a little bit less clear of a picture. It's kind of showing the area where we see the low seismic velocities and the low density is kind of maybe a transitional area on the border between the more resistive stuff that's beneath the geysers, all of those cooled plutonic rocks, and maybe something else that's more conductive extending in that northeastern trend. From the Clear Lake area kind of up towards the Sutter Buttes area. So there's definitely some interesting things to kind of think about and unwrap there, and that's really what we're focusing on going forward, is finishing up this work with the MT inversion so we can really feel good about our MT inversions and those resistivity maps that we have there, and then trying to integrate many of these different types of geophysical data in one joint inversion so we can get kind of one model out that can accurately explain and reproduce all of these different types of data. Because right now, there's just certain parts of the model that these individual geophysical inversions don't do a good job of constraining. So we're just trying to bring everything together and get as holistic of a view of it as possible. I think that may be it for me. Next slide, please. Yeah.
All
that's
right.
it for me.
Good afternoon, everyone. I know it's that time when everybody gets a little sleepy and we're in a dark room and it's cool. I am going to talk to you a little today about the work that I'm doing, which focuses on things that go boom. So I work on the physical volcanology, which is the eruptions on the surface. And if you'll click on that slide one more time, hit the next. So physical volcanology is really often concerned with hazards. Volcanoes erupt, they're dangerous. Why do we care about hazards in Clear Lake? It's got pretty old volcanic rocks, except for the very youngest stuff. When you talk about volcanic rocks in the millions of years, you may not see that again in your lifetime. When you're starting to talk about volcanic rocks in the thousands of years old, there's a possibility that that might be activity we could see again in a human lifetime. So if you go to the next slide, why are we studying hazards? One of the youngest features in the Clear Lake volcanic field is this really interesting volcano called a maar. And maar comes from a German word. It's very specific to a region near the Eifel area of Germany. And it is a word for a round crater lake. And they have a bunch of them there. And what they figured out is that this is a type of volcano that forms when you have magma rising to a shallow point in the earth and it hits groundwater. And magma is very, very hot. Water is much, much cooler than magma. If you put a hot thing into water, it's going to form steam and explode. And sometimes those explosions are violent enough that you actually form a crater. Now, you'll notice that these are pictures here that look a little bit like the Clear Lake area, but they are not. The top picture on the right side there is actually Lake Mývatn in Iceland. And the bottom one on the left there is, I believe, an example of one of the Mars in Italy. So we actually find these all over the world, but the same processes are happening. We're getting explosions very close to the level of the ground, or in this case, the level of Clear Lake itself, which has been here for a very, very long time. You have these eruptions that form when the water and the magma interact and explode, and you get a maar volcano. And if you are familiar with places like Soda Bay, Horseshoe Bay, all of those sort of scallopy places on the shoreline of Clear Lake, these are places where we have these maar craters. So if you go to the next slide. So this is what a maar eruption looks like from a sideways view. This type of eruption usually lasts only a few days to a few weeks, so it's really short-lived in volcanic terms. It's actually, it is explosive, so it throws plumes of ash and rock. So volcanic ash is actually sand. It's not like burned ash. It's just pulverized rock. These can go up about 5 to 10 miles in the air. So on a volcanic scale, not super big. When you get deposits from these, when all of this falls back down on the ground and sits there, you get also things like pumice. So pumice, if you've ever used a pumice stone on your feet, very frothy, very light, little popcorny looking thing. That's because of all the gas and the steam that forms in these explosive eruptions. So you get these frothy pumice rocks. With these maars, you're also ripping up rocks that are already there. Sometimes it's as the magma's rising through the earth. Sometimes it's because the crater that it's forming, you're throwing those rocks out of the crater. And so not only will you see the stuff we call juvenile, the new lava coming out, you will see bits and pieces of the rock that was already there, like the lava flows from Mount Konocti, or the Franciscan Formation and Great Valley Sequence, the sedimentary and metamorphic rocks that are already here. And the interesting thing about these maar volcanoes is they're basically a one-and-done situation. They erupt once, they have maybe a few days or weeks where they have multiple explosions happening over and over and over again, but they don't erupt from that same crater. So Soda Bay is never going to erupt again, or if it does, it would be really, really unusual. So these are volcanoes we call monogenetic, one genesis. So next slide. And this is what it looks like in real life. This is the eruption of Ukindrik Maar in Alaska in the 1970s. And so you can see you've got that crater basically right at the ground surface. You've got a big old plume of ash. You can see all of that light stuff on the ground around the crater, which is maybe, I don't know, less than a mile wide, something like that. That's the ash and the rocks that are being thrown out during this Maar eruption. So next slide. Okay, again. Again, we had some little animations. So Clear Lake does have these young maar volcanoes. And on the upper right there is a map with the topography, and you're not going to see any of the roads on there, but it's also got those little circles, which are where all of these maars that we know about are located. Obviously, Soda Bay and Horseshoe Bay are very nice and rounded. They look like craters already. But we've got Little Borax Lake, right in the middle of the Buckingham Golf Course, is actually a maar volcano. And we think that there are more in Konocti Bay and out along the Clear Lake Oaks area and the Arm. And pretty much anywhere that you see a scallopy shoreline, I get suspicious and think there might be a maar there. So that's a beautiful shot from up on Buckingham Peak of that nice round crater in the golf course, and then also off to the left where we have our bays. So next slide. And this is what those deposits look like when they come out. Basically, if you've ever seen a person standing on the side of a road in a road cut staring at a wall of popcorn, that is a Mar deposit. It has lots of these little pumice pieces in it, lots of little tiny chunks of the local rock that's come up, and it's very distinctly layered. So that one on the top left is actually from the bottom of one of the scoria cones up north of the lake, one of the quarries that you've got for road material, and that started out as a Mar eruption. So that's why it looks so light and sort of frothy looking. There's all those beautiful layers. So that area was wet when it erupted, and that magma came up through there. So we got a Mar, and then it became a scoria cone, made all those nice cinders that you might use in your landscaping. And there are a couple more examples from different areas, mostly on the southwest side of the lake. There's beautiful layers there. You can see the popcorn on the bottom right next to that yellow notebook. And that is me pointing at a little layer of black material in the Mars. One of the ways that we can tell how old these Mars are is by finding organic material in the deposit. So not necessarily burned stuff, but that would be the ideal. Little bits of plants, little bits of peat that come up from inside the lake or from the marshy bits of the area. And we can carbon date that because these Mars are so young to begin with. So next slide. So when we carbon date that, it's a similar method to the one that Seth uses to date much older rocks. You're depending on the decay of specific forms of the atoms of carbon. We find that the youngest Mars, so the ones up in the little red dots right there, years before present is on the left, and our youngest Mars are somewhere between 15,000 and 10,000 years, and we've actually got even some new dates. The youngest one is about 8,000 years old. So, as volcanologists, when things get to be younger than 10,000 years, we start paying attention. We say, this volcano is probably still active. Might not be active in our lifetimes, but it is worth keeping an eye on. And we do keep an eye on the volcanoes here. We have monitoring systems, we have seismometers watching earthquakes, we watch whether the ground is moving up or down, and we also look at gases coming out of some of the areas like the sulfur bank mine down the other end of the lake. So next slide. So, you might ask, do we need to worry about these volcanoes? 8,000 years old is pretty young on a geologic time scale, but the answer is, if you'll click again for me, right now, no. We are not going to have a situation like these volcano disaster movies. We do look very carefully at monitoring signals like I just mentioned, and the whole reason that we're out here doing these geologic assessments are basically like building up a medical history for the Clear Lake volcanic field. The more you know about someone's medical history, the better you can predict what might happen in their future. So if you have a medical history of heart attacks in your family, you know you want to take care of your heart health. And we build up our history of the volcanic field, and then we also take the pulse with our monitoring. So the better we know our patient, the better we can predict when volcanic unrest might happen or is happening and means something important. So you shouldn't worry about it right now, but we are out here keeping a very close eye on things all the time. So next slide. So that is why we are out here building things like our hazard assessment. We are working on an interactive website with a map on it where you can actually learn about a lot of the different rocks and features of our field. We will be publishing some fact sheets soon that you could potentially bring to your vineyards or your tasting rooms and have available for people. We're here doing outreach, obviously. And we are going to continue to study these volcanic fields in the coastal areas of California because it's really important to know the full history of this progression of volcanism on our coast. But I'm talking to a lot of people who are interested in wine growing. So I threw a little bit in here. Being an East Coast girl, I thought I would try and tell you about your own profession, which is not something we do that much out here. And if you go to the next slide, I wanted to point out that our volcanic history here is really intimately tied to the viticulture that goes on. Your viticultural appellations are because you have these unique volcanic rocks and volcanic soils. And so I thought I would tie that back a little bit to the geologic map that we talked about briefly. So if you go to the next slide, Terroir, you all know about it. It's something that we don't think about a lot as geologists, but it really makes sense for us because the geology of a place really has strong controls on the topography, the shape of the landscape, and thus on the soils that you get in a specific place, the way the groundwater moves through it. All of these things are actually closer than we think about a lot of the time. These are some basic connections that you can draw between the different things. The different rocks in this volcanic field obviously are going to affect whether it's appropriate to go grow grapes in a particular place, and also what kind of grapes do best there. So next slide. So I pulled this from your wonderful website. It's a very beautiful depiction of all of your wine growing regions. Of these wine growing regions, the Big Valley, High Valley, Kelsey Bench, and Red Hills regions are really the ones that have some volcanic influence involved. So if you'll go to the next slide, I thought I would pass through some of these. Your Big Valley area laps up onto the slopes of Mount Konocti, which is our lava dome complex. These are dacite volcanic rocks, so they have a lot of silica in them. They're sticky and pasty when they erupt, and they're explosive. But they are also right on the edge of this, your broad valley with the sedimentary and metamorphic rocks underneath it. And so it's kind of interesting that you've got Mount Konocti there has created a topographic high that is shaping the climate and the valley that's formed in this area. And if you will go to the next slide, please. Kelsey Bench, we start to get into more of the lava flows and the pyroclastic or the explosive volcanic deposits from Mount Konocti. If you can see on the map there, you're starting to get into those purples and oranges. Those are rhyolites, which are a very, very glassy, silica-rich rock. You've still got some of the alluvium. You've got the Kelseyville Formation, which has a lot more sandstone and mudstone. So those are sedimentary, not necessarily affected by the volcanics. But the next slide, you get into High Valley. And one of the really interesting features of High Valley is that it was basically dammed by a lava flow. So Round Mountain, you've got these lava flows which have cut off a drainage, a stream drainage, put in, caused all of that alluvium, all of those sediments to gather there, and made this into a really great region, obviously, to do some viticulture. But that is one of the younger features, volcanic features, lava flows and a scoria cone in the Clear Lake volcanic field. So that's something that we spend a fair amount of time looking at. And the next slide. And then, of course, we have Red Hills, which is really where we get into the heart of our volcanic field. It pretty much, as Seth said, spans the range of volcanic rocks from the really glassy silica-rich ones all the way to the really magnesium and iron-rich ones that give the Red Hills their characteristic red soils. So everything from rhyolite to basalt. And this is where we spend a lot of our time. So you can see here you've got all these different colors from the geologic map. You've got faults all over the place. And so this is just a geologist's paradise, and you'll see us out here quite a bit. And then I think, if you go one more. All right, so we've told you a lot about what we do, but what our success really depends on is working with you in this area. As Seth and Mike said, you've given us this amazing access to things that we're studying. And because we do work on hazards and we do work on how people live with volcanic eruptions and hazards like that, it's important for us to also ask you, how can we work with you? What things would you need to know from our research that might be useful? If there ever were to be any kind of volcanic activity, what would you need to know? Volcanic hazards can have really big impacts on agriculture. And so that is why we are here as an observatory. We are here to help people deal with volcanic hazards. And also, who else should we be talking to? A lot of the time we go out and knock on doors, or we see you at the side of the road or at a road cut, and that is a great way to make connections. But you know this land better than any of us do, and it's really important for us to learn from you when we're doing our work, where we can do our work, and how we can do a really good job at it. And I believe, if you go to the next slide, That is the end of it. We are absolutely happy to take questions, and we know you've thrown a lot of technical stuff at you. We have our emails up there. We're always happy to get in contact with anyone. And we are up here pretty much all the time, winter, summer. So if you see us, we love to chat. And I will stop there.
Got one question. I guess we pump water up to the geysers, wastewater, I guess. What is that doing to volcanic activity potential, if anything?
Volcanic activity, not much. There's not really any way for pumping water in the ground to affect a volcanic eruption. You need a lot of water, like you need a whole, subterranean lake, basically, for it to do something like create these Mars volcanoes. It does have effects on earthquakes. Water and faults can make them slip more easily. The geysers, they know, and they do have lots of little earthquakes all the time. It's also super well monitored. So when we do think about the hazards from that is when you're starting to maybe put a new geothermal well into a new area you haven't been before. It's kind of hard to figure out sometimes where the faults are, and if you hit a fault, and put water into it that you didn't know about, that's when you might have to think about it. But volcanoes, not an issue.
The main thing that they're doing there is they're replenishing all of the water and all the steam that they've pulled out of the steam reservoir since they started producing in the 70s. Because for the first 40 years, they just took steam and they've put hardly anything back. So in order to keep that field producing and to keep it a viable resource for producing electricity, they need to be putting water back in to produce more steam so that they can keep the cycle going.
Yeah, I have a couple of questions. Is it my turn? Yeah. The first one is you mentioned the Mars are a one and done thing, monogenetic.
Yes.
And it's kind of counterintuitive. You think of Soda Bay still underwater, so what if the magma comes again? So that's my first question.
Right. So Soda Bay, as you know, was probably named because there's all this carbon dioxide coming out of it. You can have an eruption and then still have heat and gas underground where that eruption happened and still have that bubbling. Super common. It is a faint possibility that you could have magma come up in that same spot, but I like to think of magma as lazy. It wants to take the easiest route to the surface. And if it can go somewhere else where there's not already a big old cold plug of cooled rock, it's going to go around that. And since there's so many faults in the Clear Lake area, if we have another eruption, it's probably going to be elsewhere along one of those faults.
Gotcha, I get it, from the plug. The other question is, earlier in the presentation was mentioned that the St. Helena area, Mount St. Helena and maybe Cobb also are 3 million years old, versus Clear Lake, Konocti, Mount Hana are much more recent, and there might even be like a plume of molten rock underneath, we don't know for sure. But my big question is that whole area in, obviously it affects Sonoma and Napa, but also the Middletown area. How would that affect the current soil? You mentioned all the volcanic properties for grape growing, so how about if you have an older volcano, what does it mean?
In general, it means that the soils are going to be better developed. So the longer the volcanic rocks sit around, the longer they have to break down, turn it into something more soil-like than like gravel-like. I'm not as familiar with viticulture as I should be. You'd probably want a soil scientist for that. Maybe Seth wants to take a stab.
No, I think it's dictated, the differences are led, if all other conditions are held the same, by time. How long do you have to develop the soil? But if all conditions aren't the same, like the composition of the rock is different between one spot and another, those rocks might be the same exact age, and you'd have very different soil profiles. So I think the nuanced differences between different soils is a result of time and also composition of the rock, where it's sitting, is it in a valley, is it up high, all those kinds of things.
Thank you.
Wait for the mic.
The previous question was about the potential. It has some potential for volcanic activity, but I would suspect that the gas removal systems at the geysers might alleviate some of that volcanic activity because you're moving all that gas out of the formation. Any thoughts?
As
Yeah.
Jess said, the activity, the pumping of water into the geysers doesn't represent some significant change to any volcanic system or the
Correct.
potential for volcanism.
Very shallow.
The injection of water at the geysers is creating seismicity, quite shallow, but it's not affecting the volcanic system or the potential for eruption.
Yeah.
Yeah. I work at the geysers, but my question is, since when they remove water, to turn turbines, right? They're also removing a lot of gas. So is that gas removal system at the geysers help? Because you're like alleviating pressure.
Right. So we've actually had people ask us this question about Yellowstone. So we all know that Yellowstone has geysers all over the place, big hydrothermal system. It's a very active volcano. People have proposed drilling and starting up geothermal operations there as a way to release the pressure. Our human operations on a volcanic system are so minuscule compared to the whole thing that it wouldn't have enough of an effect. The forces and the amounts of gas involved are so huge. So, I mean, if you wanted to drill 1 million holes in it, you probably could remove enough of that water to have some effect, but in terms of an eruption, it's going to happen whether or not you do something.
Okay, thank you.
Just curious, you go to work on Monday, things are changing. What kind of ominous signs are you looking for that we need to sell our properties or whatever? Between the three of you, what are you looking for that would indicate something bad?
So that goes back to the monitoring. So you look for little earthquakes happening in the ground. So imagine that you had a bit of magma rising. In fact, if any of you watched the news this morning, you might have seen that Kilauea volcano in Hawaii is erupting again. There's a lava lake forming at its summit. What they saw before that was tons of little earthquakes. And if you can figure out the three-dimensional position of those earthquakes, you can actually watch them rising from deep to shallow parts of the crust. You look for changes in the level of the ground or the shape of a volcano. And this is something you can see with GPS. We actually have this big, wide network of really, really sensitive GPS sensors, like the ones in your phone, but way, way better, that can tell us down to the inch how much the ground is moving, or if it's moving at all. So when you shove magma up under the ground, it makes it swell. You can see it in these sensors. You can actually see it from satellite data. And then we look for gas. So if you suddenly have, a mud pit or a steam vent pop up in the middle of a field, that's a good reason to get suspicious. This is something that happened in the 1940s in Mexico at Paricutin volcano, the volcano in a cornfield. If any of you watched Reading Rainbow a long time ago, they actually had an episode about this. This poor corn farmer, saw these ground cracks form in his field, and the next thing he knows, there's steam coming out, there's lava being thrown into the air, and suddenly he's got a 500-foot-high volcano in his cornfield. So I would look for, change if you're suddenly seeing steam coming out of the ground where there wasn't any before, big ground cracks that can't be explained by a drought, lots of earthquakes, and all of these are things that we would look at if we were going out to evaluate it. And we are happy to hear from people who are noticing unusual things. We've come out of here a few times for folks who've been feeling earthquakes on their properties, or they see ground cracks that they're suspicious about. That is part of our jobs, is to come out and look at it, see what it is, reassure you hopefully that nothing is going to happen.
Scare you to death and then put you in touch with our realtors.
Exactly. Yeah.
really be a quick one, but talking about the seismic activity induced by the activity at the geysers, last Thursday, 5 a.m., there was a 4.4 magnitude earthquake 9 miles north of Geyserville. So this type of magnitude, is this possibly it's the geysers or it's something else?
It is, yes. It's not the usual. Most of the earthquakes of the geysers are something like magnitude 3 or below. You really can't feel them that well unless you're nearby. But it's not uncommon to see those magnitude 4s.
A couple a year probably they get
Yeah, a
up there?
couple a year. If we saw a bunch of them all at once, then we would start being concerned. But the way that the larger earthquakes work, if they get big enough, not only do you have the initial earthquake, you also have more little pops afterwards as the ground adjusts itself. So it's not unusual to get these little swarms of them from time to time.
What's the Franciscan complex? I saw it a few times.
Sorry, we use that term a few times. So it is rocks that were formed by all of those tectonic forces that you saw sort of squishing and deforming and shoving California northward. There's things like serpentinite, so those really shiny green rocks you see out there. There are cherts, so if you see, you know, that sort of jasper is the common name, these really red, blocky pieces of rock. There are even these sort of dirty sandstones in there. They're called graywacky. But it's all stuff that has been crunched up and heated up and basically changed from what it originally was. And you might see 5 or 6 different kinds of these things in the same area. But yeah, if you see anything that looks blue or green on the ground, that's probably Franciscan complex.
I have a good analogy for this. You got a subduction zone where one plate is being shoved beneath the other. Think about having a piece of bread with a bunch of peanut butter on it, and you've sprinkled, raisins and olives and pecans on that peanut butter, and then you shove the piece of bread down beneath the table, and all that stuff piles up against the edge of the table. That is what California's coast is made of. These volcanoes have erupted through that and onto that.
Yeah.
So it's a whole bunch of different rocks, like Jess said, all juxtaposed against each other in a matrix of stuff that was scraped off the ocean floor.
Yeah. You might also hear it called melange, which is geologist speech for this is a mess and we don't know what all is in it. All right. Are we good?
Yeah. Oh, yeah.
Thank you.
Good time.
Oh, we have one more question.
Mount Konocti, volcanic. Mount St. Helena, volcanic. Mount Hanna, volcanic. Round Mountain, volcanic. What about Snow Mountain up north?
Ooh.
No, not volcanic. Snow Mountain is a bunch of rocks within the Franciscan Formation. I'm almost certain it might be the Great Valley sequence. Those are two big, like 120 to 80 million year old basement rocks that have been uplifted along the major regional faults in this area. Yeah, so Snow Mountain not made of volcanic rock, but uplifted by the same processes that have uplifted Mount St. Helena, for example.